Good afternoon to everyone. Thank you for being here until the end of the conference. We are almost over. So now we are going to introduce the last keynote speaker from the Latin American Conference on Statistical Computing, and then we'll have the last keynote speaker for CIMAC. So it is my great pleasure to introduce Professor Francisco Cribari-Neto. Francisco is Professor of Statistics at Federal University of Pernambuco in Brazil and is the Vice Director of the Center for Exact and Natural Sciences at the same university. In the past, Francisco was President of the Brazilian Economic Society, and he has made a great contribution for statistics in Brazil. He had several roles, several major roles at CAPES. CAPES is one of the Brazilian national science agencies. Professor Cribari has published more than 120 research papers and has supervised more than 60 PhD and master students. Today, Professor Cribari will be talking about a new log linear bimodal birnbaum-saunders regression model with application to survival data. Thank you. The floor is yours.
Thank you, Paulo, for the nice introduction. And I would like to thank the conference organizers and the University of Costa Rica for the invitation. And I'm going to present a new regression model that I developed recently. And this is a fairly long paper, and it's fairly technical, so I'm going to skip some technical details so that I can present the main idea of what we do in this paper. There is a distribution called the birnbaum-saunders distribution for positively valued data, for data that takes values that are greater than 0. And it was introduced in 1969, and it has been quite used in the next 10 or 20 years. And it's a nice distribution because it was derived from some physical phenomenon. And the problem is that there was an equipment that would fail after the development and growth of a crack under cyclical pressure. And this distribution proved to be very useful to model other data, like data in biology. And some regression models based on this distribution were proposed in the literature. The most famous one is this one by Rick and Nelderman. It was proposed in 1991. And what we do in this paper is to generalize this model, and we propose a new model that generalizes this model. So there were several papers recently that investigated the birnbaum-saunders distribution and also birnbaum-saunders regression. And if anyone is interested in this area, I recommend this new book by Victor Leiva, his 2015 book, which is a review of birnbaum-saunders models. So what we are going to do is to introduce a new regression model based on a generalization of the birnbaum-saunders distribution, which is particularly nice for one reason. It can be bimodal. The standard birnbaum-saunders distribution cannot be bimodal. And the distribution that we work with can be unimodal, and it can be bimodal. And that's a nice feature. So what, let me go forward. So we introduced this regression model, and then we developed point estimation, confidence interval, hypothesis testing, diagnostic analysis. We propose a test for correct model specification, and we propose residuals for the models, and so on. So we propose the model and we develop a statistical inference for that model. So we start with the birnbaum-saunders distribution, which is the basic distribution that we work with. And then we take a generalization of that distribution that has 3 parameters. It has eta, which is a scale parameter. It's also the median of the distribution. And the other 2 parameters, alpha and E, are shape parameters. And that's the density. And this distribution can be used to model data that is positive valued. So that's the distribution that we are going to work with. And the interesting thing is that when those last 2 parameters, alpha and E, when they are greater than 2, the distribution is bimodal, which is a nice feature of this distribution. So here are some density plots. And I don't know if you can see, but probably not. Here we have one bimodal density here. So the distribution is very flexible, and it can accommodate bimodality. No? When alpha is greater than 2 and E is greater than 2, the distribution is bimodal. No? And this distribution has several interesting properties. One of them, if I have a random variable that follows the distribution, and I take 1 over that random variable, it also follows that distribution. So it's closed under reciprocity. So if T follows the generalized birnbaum-saunders distribution, 1 over T is also distributed as GBS with parameters alpha and E, the same parameters, and the median is 1 over eta. Eta is the median of T. And also, if you multiply T by a constant, you will still have a random variable that's GBS distributed, alpha and eta are unchanged, and alpha and E are unchanged, and eta is multiplied by A, which is another nice property. And it's very easy to generate pseudo-random numbers from this distribution because it's related, the distribution is related to the standard normal distribution. So if you can generate pseudo-random numbers from the standard normal distribution, you can generate pseudo-random numbers from this distribution, which is nice also. The moments of the distribution are somewhat complex, and that's the expression for the art moment, but we are not going to need that. An alternative representation of this distribution, it's very interesting, is this. If you take the log of your random variable, so T follows the GBS distribution, but if you take the log of T is distributed as hyperbolic sine normal. And that's very interesting because we're going to use that to create our regression model. So this distribution is related to several distributions in interesting fashion. And what we're going to do now is to use this distribution to introduce a new regression model. We are interested in studying the behavior of Y, but Y is affected by X. So X are the regressors, the covariates, the independent variables. And Y is the log of T, and T is distributed as GBS, the Generalized Birnbaum-Saunders distribution. And beta is a vector of unknown parameters, and epsilon is a random unobserved error. And we want to estimate and make inference on beta because beta measures how the covariates impact the variable of interest. And that random arrow over there follows the hyperbolic sine normal distribution. And then how do we estimate the parameters? We use the maximum likelihood method, which is the most commonly used method in statistics. So we write the likelihood function, and we take the log of that function, and then we need to maximize that function. In order to do that, we need to use an optimization algorithm, a Newton or quasi-Newton algorithm, and then in order to use that algorithm, you need to specify a starting point, and then the algorithm goes on from there. And then we make a proposal of starting points for the nonlinear optimization. For beta, we use the standard classic least squares estimate, x prime x inverse x prime y. For ni, we use 0.5 because 0.5 means that the generalized birnbaum-saunders distribution reduces to the standard birnbaum-saunders distribution. And then we take the derivative with respect to alpha, set that equal to 0, replace the other parameters by our initial choice, and then we get this expression for alpha 0. So that's how we propose that one starts the optimization algorithm. And then after you maximize the log likelihood function, you get your point estimates. We know that maximum likelihood estimators, when the sample size is not small, are approximately normally distributed, which is nice because we can use that to construct confidence intervals and to perform hypothesis tests. And the asymptotic covariance matrix of our estimator can be approximated by minus the Hessian matrix. And I'm not going to present here, but in the paper, we give a closed form expression for this matrix, for the Hessian matrix. And then, using this result, we show that it's very easy to construct confidence regions for the parameters and also to construct individual confidence intervals. And we are not able to derive the expected information matrix, and then we work with the observed information matrix. And suppose that you have a bunch of parameters and you want to make inference on one or two of them. You don't want to make inference on all of them. And then we partition the parameter vector theta into two vectors. One of them is the vector of parameters of interest. Those are the parameters we are interested in. And the other one is the vector of nuisance parameters. So suppose that we want to test a hypothesis on a subset of theta, and that's very easy to do that. We can just use the standard likelihood ratio test. We maximize the log likelihood function and get theta hat, and then we maximize the log likelihood function, imposing the null hypothesis, and get theta tilde, and then just compute the test statistic. And when the sample size is large, this test statistic under the null hypothesis follows approximately a chi-square distribution. If you are testing a restriction on one parameter, that's chi-square with 1 degree of freedom, 2 parameters, 2 degrees of freedom, and so on. So it's very easy to perform hypothesis testing inference. We also propose a pseudo R-square measure that measures the goodness of fit. It's this R square N. It takes values from 0 to 1. The closer to 1, the better the model fit. And how we compute that? L evaluated at theta hat is the likelihood function evaluated at the maximum likelihood estimator. And L0 is the likelihood function for the model with no covariates and only the intercept. So we basically, and N is the sample size, is the number of observations that we have at hand. So we just compute that measure, and that assumes values between 0 and 1, and the closer to 1, the better the model fit. And we also develop residuals and diagnostic analysis. We propose two different residuals for this model. The first one, that's RSHN, uses the relationship between the normal and the sine hyperbolic normal distribution. And if your model is correctly specified, that residual is expected to follow a standard normal distribution. We also propose what's known as Cox-Snell residual, and it's also very easy to compute, this RCSG, and if the model is correctly specified, that should follow a exponential distribution with unit mean. So those residuals can be easily computed. And then in the paper, we also give an algorithm that you can follow to construct what's known as QQ plots. So you plot your residuals, empirical quantiles against the asymptotic quantiles with some envelopes that are confidence bands, and you expect that most points fall inside the envelope. And then we give a simple algorithm. I won't go into details, but it's very easy to use the algorithm and produce the plots. And by looking at the plots, you have an idea whether your model is correctly specified. We also develop local influence analysis, which the main idea is very simple. I'm not going to go into the details. The main idea is very simple. You have your data, you have your likelihood function, and you are going to introduce a small perturbation in your likelihood function or in your data. And you expect that if this perturbation is small, the estimates won't change a lot. And then you are going to get a measure for each observation, and you will try to identify if there are observations that when you perturbate the model very locally, those observations cause large estimates changes. So we work with that likelihood displacement, and that lowercase omega over there is the perturbation vector. Lowercase omega 0 is the vector that gives no perturbation at all. In some cases, it's a vector of ones, and in some cases, it's a vector of zeros. Okay? And then to compute that, we need to find the maximal eigenvalues of a matrix and the corresponding eigenvectors. And in order to compute that, we basically need two things. We need capital delta, which is a matrix of cross derivatives here. Those are the elements of capital delta. And we need the Hessian, which we already computed. I did not present the Hessian, but it's presented in the paper. So if we have those two things, we can set up different perturbation schemes, and then we can compute the measures. And then we do that in three different ways in the paper. We do the first The first way is case weights perturbation. We basically have our log likelihood function is a sum of a bunch of things. L1 plus L2 plus L3 and so on. I'm going to do lowercase omega 1 times L1 plus lowercase omega 2 times L2 and so on. So the vector of no perturbation, the lowercase omega 0 would be 1, 1, 1, 1. And then for that perturbation scheme, we already have the Haitian, then we derive the delta matrix. And then after that, we consider a second perturbation scheme, different perturbation scheme, where we replace each response value by that response value plus omega I times a scaling factor. So we introduce the perturbation in the response, and then we derive that capital delta matrix for this case. And then we introduce perturbation in the regressors, in the independent variables, and then we compute the delta matrix. At the end of my talk, I'm going to show that this thing here that looks very ugly is extremely useful using a real data set. And then we also compute generalized leverage matrix that if you take the diagonal elements of that matrix, they will give you an idea of how atypical your observations are in the regressors space. So we need to compute that matrix. We already have the Haitian, so we need to get those other terms there, L theta y and D theta. L theta y is basically a matrix of cross derivatives involving theta and involving y. Right? And then after a long and tedious algebra, always spare you the details, we arrive at a fairly simple expression here. You see? We define V as a diagonal matrix, so it's very easy to work with diagonal matrices, and that's basically X times the inverse of X prime Vx times the transpose of X times V. So that's very easy to compute. You basically need to define the matrices, and that's it. Another inference tool that people like to use is what's called Cook's distance. And the main idea is very simple. Suppose that you have 50 observations. You remove the first observation and see how much your estimates will change. You remove the second observation and take a look at how much your estimates will change, and so on. And then you use that formula. Theta hat I means that you computed your estimates without the ith observation. And in order to do that, suppose that you have 1,000 observations. You are going to need to maximize the log likelihood function 1,000 times, so that's very costly. So we follow a proposal in the literature to take a one-step approximation and then avoid having to maximize the log likelihood function n times. And using this approximation, we give a fairly simple expression that one can use to compute the generalized Cook distances. And then you are going to have one number for each observation. So suppose that the observation of number 17 has a high number, a very large number associated to it that indicates that that observation is an outlier, an atypical observation. And then we also give expressions. Suppose that you are only interested in the estimation of beta, you can use the first formula. Suppose that you are only interested in the estimation alpha, you can use the second one, and so on. We give also disaggregated expressions. We also developed in this paper a specification test. I won't have time to go into details, but the test that we propose is very simple. The null hypothesis is your model is good. It's correctly specified. The alternative hypothesis is that your model is misspecified. I don't know what's caused in the misspecification, but your model is misspecified. And then we start with a test that was proposed for the classical linear model called the Ramsey reset test. And then we developed a variation of that test for our model. But it's very easy to do this test. You basically fit your model, you get the fitted values, and you add powers of the fitted values as extra covariates, and then you test the exclusion of those extra covariates. If those extra covariates prove to be useful, your model is no good. And then we show that. We also develop prediction intervals, and I won't go into details, but the idea is very simple. Suppose that you have 100 observations on Y and 100 observations on X. Then you can use the model as I presented. But suppose that you have 100 observations on your regressors and only 99 observations on Y. There is one missing observation for your response. And then you can predict that using the corresponding fitted value. But what happens if you want to construct a prediction interval for that missing observation? And then we developed here Bootstrap resampling-based prediction intervals. And we basically consider two Bootstrap methods. One is called percentile, and the other one is called BCA. And the interesting thing is that in the BCA method, you need to estimate Z0, and you also need to estimate another constant, A, which is more difficult to estimate. But in our paper, we proved that for this model, A equals 0. So that simplifies computation a lot. And then we give Bootstrap algorithms that one can use to construct prediction intervals for the missing response values. And then we also address the issue of model selection. Suppose that you have Y, that's your variable of interest, and then you have 15 or 20 potential regressors that you could use to explain Y. How do you select which ones should enter the model and which ones should not enter the model? So most people do that using model selection criteria, and that's what we do in the paper. The most well-known model selection criteria is the AIC that was proposed by Akaike in 1974. And he basically estimated the discrepancy between the candidate model and the true model, and that plus 2K over there is an asymptotic bias correcting term. And this model selection criteria doesn't perform very well in practice, so some people propose the AICC, which is a corrected version of the AIC. And there are some Bootstrap variants of the AIC that were proposed in the literature. We consider 5 of them, and as you can see, the way that they work, they use Bootstrap resampling to estimate that bias correcting term instead of just using 2 times K. And we also consider model selection criteria that I proposed with a former PhD student of mine, Fabio Bayer, that was published in 2015 in Test. And we use Bootstrap not to estimate the bias correcting term, but to estimate the discrepancy between the candidate model and the true model directly. And that's what we call BQCV. And we also consider this 632 QCV, which is a weighted average between the BQCV and the standard estimate. And we also consider several other criteria, such as the Schwartz information criterion, which is also known as BIC or SIC, Bayesian information criterion, the Hanna and Quinn, and their corrected versions. And we use all of that in the Monte Carlo simulations. And I'm going to go fast here because I'm going to just present some Monte Carlo simulations that we did. And we estimated the parameters, maximizing the log likelihood function using the BFGS method with analytical gradient. And we basically generated 10,000 data sets and estimated the parameters 10,000 times. And here are the relative biases. As you can see, the estimates of beta are nearly unbiased. When the sample size is small, the estimates of alpha and E have some bias. I'm not going to present here, but we did simulations with Bootstrap bias correction and works very well even with small samples, so you can reduce that bias using a Bootstrap bias correction. And we also did simulations to see if the residuals that we propose in the paper are reasonably approximated by their asymptotic distributions. And then we have different schemes here, E1, E2, and E3. Those are different data generating schemes. And the first row is the residual that should be approximately standard normal. So the mean should be close to 0, standard deviation close to 1, asymmetry close to 0, and kurtosis close to 3. And the second row is the residual that is expected to be exponentially distributed with unit mean. So those numbers should be close to 1, 1, 2, and 6. And you see that the residuals are well approximated by the corresponding distributions, so they can be safely used. Now we present some Monte Carlo simulations on the test for correct model specifications. And I'm going to just show some size and power results. Here we generate the data from a correctly specified model. And you'll see, for instance, at the 10% significance level, as the sample size increases, the empirical size gets very close to 10%. With 90 observations, you have 12%, 12.6 instead of 10%. So the test is working well. And can the test detect incorrect model specification? Then we generate the data using 4 different misspecification errors. Those are marked in red. We failed to include in the model an interaction. We failed to include in the model a squared regressor. We failed to include in the model an extra regressor. And in the last one, the true data generating process is nonlinear, and we estimate a linear model. So those are 4 specification errors. And as you can see, for instance, in the last one, with 90 observations, the test will tell you almost 84% of the time that your model is incorrectly specified. So this test seems to have power against different kinds of misspecifications. And then we also present simulation results on the prediction intervals that we develop in the paper. And as you can see, for instance, the nominal coverage is 95%. So nearly 95% of the time, our intervals include the missing response. So they seem to be working well, both BCA and percentile. And then we present results on model selection. I won't have much time to go into it. But the criterion that worked the best was the corrected BIC, the corrected Bayesian information criterion, or corrected SIC. For instance, with 60 observations, the criterion selects the correct model nearly 94% of the time. So it's working extremely well. And model selection criterion works well. And then the last part of the paper, I'm going to spend my last few minutes on this part, is an empirical application. We got a real data set, and we try to analyze this data set, which is a well-known data set using our model. The variable of interest here is lifetime in weeks of patients that were diagnosed with severe leukemia. And the regressors are the white blood cells count upon diagnosis, and also whether the patient was AG positive or AG negative. And those are the two covariates that in principle should be able to explain the patient's lifetime. So we are going to work with the log of the survival time and with the log of the white blood cells count, and X3 is a dummy variable that indicates whether the patient is AG positive. And if you look at those plots, for instance, the one in the middle, you'll notice that patients that are AG positive tend to live longer than patients that are AG negative. So we expect X3 to be important in explaining the behavior of Y. Right? So let's see if that happens. The problem is that when we estimate the parameters of the model, look at what happens to beta 3. Our estimate of beta 3 is 0.055, and the standard error is 0.27. The standard error is very large. That indicates or that suggests that X3 is not relevant for explaining why. And that's puzzling, because if we just look at the graph, X3 seems to be relevant. So I'm going to come to that later on. And even if, when you remove X3 from the model, your BIC or SIC improves. So the SIC is also saying that X3 should not be in the model, which is puzzling because we just saw in the graph here in the middle panel that X3 seems to be relevant for explaining why. Right? And then we compute, we only have 33 observations in this data set. We compute the pseudo I-square, and that's 0.35. We tested the null hypothesis that eta equals half. That means we are testing the standard birnbaum-saunders model against our model. And we reject the null hypothesis. So we conclude that our model is superior to the standard birnbaum-saunders model. And then we do some diagnostic analysis. Those are the QQ plots with envelopes that I briefly outlined earlier. You see that near all points are within the envelopes, so the model seems to be correctly specified. Those are the two residuals. So most residuals are in the range that one would expect. And those are the local influence plots. Those are those plots that we need to compute that data, that capital delta matrix and so on. And here we have plots for estimation of beta, and those are the plots for estimation of alpha and E. And those are the three perturbation schemes: cases, response, regressors. And if you look at these plots, you'll notice that there are 3 atypical observations here. Patients number 14, 15, and 17. They seem to be highly atypical. They have a pattern that's very different from the other patients, and for some reason, those observations may be impacting the results too much. And then we also computed the generalized Cook's distance, and we also noticed that patients 14, 15, and 17 seem to be outlying observations. Let me skip this. And then what we did was this. We removed the atypical observations, and we estimated the parameters again. And we computed the relative change in each parameter estimate. We would like those numbers to be small. Let's see what that happens. Look at what happens here. When we remove patients 14 and 15 from the data, the estimate of beta 3, which is the parameter that's associated with the indicator function for Ag positive and Ag negative, changes over 10%. And also when we remove observations 14, 15, and 17, it changes over 10%. So probably those 2 patients, 14 and 15, which are very atypical, I won't have time to explain why, but they are very atypical, they are affecting the results. And then we remove those 2 observations and we estimate the model again, the pseudo R-square increases, and you see that beta 3 is now statistically different from 0. The standard error is 0.17, and the estimate is 0.64, and we now conclude, as one would expect, that the indicator function for Ag positive and Ag negative patients is important for the model fit. We also performed the reset misspecification test and concluded that the model is correctly specified. And the nice thing here is that this empirical application shows that it's important to perform diagnostic analysis and especially local influence analysis to detect atypical points that may be interfering with your statistical inference. And then we conclude that Ag positive patients tend to live longer than Ag negative patients, and also that patients with higher white blood cells count tend to live, tend to have lower lifetimes. And we conclude that from the analysis. And we also did the following. We have 33 observations. We removed the first one, then the second one, then the third one, and so on. And we constructed prediction intervals for each of them using the methods that we proposed, the methods that we consider in the paper, the percentile and the BCA method. And most data points, nearly all, fall within the prediction intervals. So the prediction intervals seem to be working correctly in this case. So just to finish my presentation, what we did in this paper, it's a very long paper. I did not have time to present all details, and I left some results out of the presentation. We propose a new regression model which generalizes the log linear birnbaum-saunders model, which is very well known in the literature. It's used in reliability analysis, in engineering, and in survival analysis in medicine. And that model is a particular case of our model. One nice thing of our model is that it can accommodate bimodality, unlike the standard model. We estimate the parameters by maximum likelihood, and then we derive in a closed form expression, which I did not present, for the observed information matrix I mean, for minus the Haitian matrix, we propose a pseudo I-square measure for the model. We propose two different residuals for the model. We perform local influence analysis. We derived generalized leverage measures. We derive a generalized Cook distance measure. We present a test for incorrect model specification for the model that we proposed. And we also give two Bootstrap-based algorithms for computing prediction intervals for situations in which you have data on X, but there is a missing or two missing observations on Y. And we carried out several Monte Carlo simulations and present the results also for model selection. And we presented and discussed an empirical application. For model selection, we considered several different standard criteria and also the criterion that I proposed for beta regression models for another class of models in 2015. And with that, we have a new model that investigators can use, mostly people who are interested in modeling data that is positively valued. And we developed several inferential techniques. What we did not do in this paper, because the paper was already very long, was to handle censoring schemes. So we don't work with type 2 sensor schemes and so on. But for complete data, we develop hypothesis testing, confidence intervals, diagnostic analysis, residuals, and so on. And we believe that this model may be useful to investigators that work in reliability analysis, in engineering, and also to people who work with survival data in medicine.
Thank you. Thank you, Francisco, for such a nice talk. So now I would like to open the floor for discussion. Are there any questions or comments? So when they think I have one myself, you were talking about atypical observations. Would that be possible to, because you were pinpointing them and removing them, would that be possible to create some kind of robust version for this regression model?
Yes, but in order to do that, we would have to go to ground zero again, because maximum likelihood estimation does not produce robust estimators. We would need to use some robustified version of maximum likelihood, most likely, or use some methods that have high breakdown point and so on. But the way that we did here, we are stuck with maximum likelihood, and maximum likelihood by itself is not robust against very atypical observations. Of course, you can also, if you want to keep atypical observations in your model, you can do simple things like, which is not ideal, you can create a dummy variable that equals 0 for the typical observations and equals 1 for the atypical observations, and you include that in your model, and that dummy variable will indicate that the model structure is a little bit different for those observations. So that's probably a quick fix to the problem.
Thanks. Are there questions or comments? Okay, so let's thank Francisco again.